In this video, we're going to talk about transformations of exponential functions. Before we can really talk about transformations, so we have to understand what a parent function is. A parent function is the most basic function in a given family. So for us, when we're talking about exponentials, we know we're looking at an exponential function because our independent variable x is in the exponent. So the most basic function that we can have is y equals b, some base to the power of x. So for example, I have y equals 2 to the x. This is our basic exponential growth graph. We have a table. All I've done is 2 to the power of x. I didn't add anything, subtract anything, multiply anything, divide anything. So every parent function has these general characteristics. We have a y-intercept at 0, 1. We have a horizontal asymptote on the x-axis. Our domain is all real numbers, and our range is 0 to infinity. However, when we do something to this graph, or to this function, if I add something to it or I multiply it by something, it's going to affect the way our parent function graph looks. So that's our goal, to be able to determine how is my graph going to change if all I can see is the equation. So when we're given an exponential function in this form, we know that each of these values, a, h, and k, are going to affect the graph of my parent function b to the x somehow. So a, it has two jobs. If it's negative, it's going to reflect over the x-axis. It also has another job called a vertical stretch or shrink. And we're not going to talk too much about this, but know that it can make my graph taller, I guess is a way to say it, or shorter. It's basically like taking the top of the y-axis and the bottom and pulling it this way so that it stretches my graph. So that has two jobs, but really we're going to focus on this negative piece. This h value in the exponent, so if I add or subtract something to my exponent, it's going to shift my graph to the left and right. That's called a horizontal shift. So if I see a plus sign, I'm going to go to the left, and if I see a subtraction sign, I'm going to go to the right. Anything that I add or subtract at the end, a constant outside of the exponent, is going to be a vertical shift. It's going to make my graph go up and down. And the way we kind of remember this is h is horrible. It lies to you. It's the opposite of what we see. That's what this minus sign means. And k is kind, and it doesn't lie. It tells the truth. So if I see a plus, I'm going up, and if I see a minus, we're going down. So knowing this, we're basically going to interpret what's been changed in our equation. This b, this is our base. That just tells us, are we going to grow or decay? What's my common multiplier? That's what this does. It doesn't affect a transformation. It just kind of gives us our starting value. So now let's look at an example. So if we have the function f of x equals 5 to the power of x plus 2, well, our parent function would just be 5 to the power of x. So anything that's not the base or the x is going to affect my graph somehow. So when I'm looking at this plus 2, I see that it's in the spot of where h would be, and h is a horizontal shift. So we know that this graph is going to go to the left 2. So now if we actually look at a picture of our graph to see if that's true, well, the blue graph is my parent function, and my red graph is the transformed one that I typed into a graphing calculator. And you can see that each of these points scooted over to the left too. So it worked. So let's look at another example. In this example, we have g of x equals 1/4 to the power of x plus 6. So this 1/4, first of all, I didn't really talk about this in the last example, but it tells me that we're going to have a decay function because of that base being less than 1. But then I see this plus 6. That's in the spot of k, so I know that's a vertical shift. So we know that it's going to go up 6 units. So if we look at our graph, again, the blue is our parent function, the red is the new one, and you can see that it did. Everything slid up 6 units. This is important because we know our parent function normally has a horizontal asymptote on the x-axis. Well, when I shift everything up, now I've also shifted up my horizontal asymptote, so now it's at y equals 6. So we have a horizontal asymptote at y equals 6, which will affect my range if I were to write it. So now let's take a look at one more example with a graph, and then we'll try some without. Now we're starting with p of x equals negative 3 to the power of x. So our parent function would be y equals just 3 to the x. So anything that's not a 3 or an x affects my graph. So I'm looking at that and I see this negative. That negative is in the spot of a. And we talked about how if a was negative, it's going to reflect our graph over the x-axis. So we have a growth graph, because our base is bigger than 1, that's going to get reflected over the x-axis. So now let's actually see if that's true. So again, I put these both in a graphing calculator to look at them. The blue one is our parent function, 3 to the x, and the red one is our new function, which is true, right? It flipped over our x-axis. Now I know that this graph is decreasing. However, if we look at the steepness, as I go to the right, my graph gets really steep. So that still tells us that we're growing, just in a negative direction. Because I didn't shift up or down at all, our horizontal asymptote's in the exact same spot at y equals 0. Except this time, if I'm talking about my range, it's going to go down forever. So the lowest is negative infinity, but it's going to go up and stop at 0. So our range would be negative infinity to 0. So now, let's look at some examples without checking with the graph. So here are 3 more examples. In our first one, r of x equals 2 times 3 to the power of x plus 1. It's a growth function because our base is bigger than 1. It has a vertical stretch because of our a value, and it goes up 1 because of our k value. That means because I shifted everything up 1, my horizontal asymptote is also at 1. So go ahead and take a look at the rest of these and see if you can identify kind of where each of these transformations comes from when we're looking at our graph. In our last example, we want to be able to create a graph given transformations without having to make a table. In the last lesson, you guys learned how to create a table of values, either by hand or with your calculator, and then plot those points. Well, now I don't want to do that. I want to be able to take my parent function graph and use the transformations in my equation to create a new graph. So here's my parent function, the base, y equals 2 to the power of x. So that's our parent function. So we now have this new function, y equals 2 to the power of x plus 2. So you can see that this plus 2 is the thing that's going to affect my graph. Well, that plus 2 is in my k spot. So I know that our new graph should go up 2 from the original. So that means that I can take all of my points and I can slide them up 2. So this point now scoots up 2. This point scoots up 2. This point scoots up 2. And then the other really important thing to keep in mind is that my asymptote used to be on the x-axis for a parent function. So when I slide everything up 2, it also slides up my asymptote. So there's the new asymptote. We've got our new points. So now we can create a graph by scooting along our asymptote and then whoop, scooching everything up. So you can see that everything in our graph from blue to green slid up 2. So now we're going to answer these questions based on our new graph. It's still growth because it gets steeper as I increase to the right as x increases. My y-intercept, so now I'm looking at the y-axis, is at 0, 3. Our domain still goes left forever, so that's negative infinity. Still goes to the right forever. Nothing's stopping it. But my range now, the lowest my green graph can go is 2 because that asymptote is stopping it. The highest it goes is infinity because there's nothing stopping it at the top. So my horizontal asymptote, which is my dotted line, would be y equals 2. Remember, we get that because it started at 0, but when I slid everything up 2, that affected my asymptote as well. So these are now the key features of our new graph, and I got them without having to create a table. I just got to scoot my points around. And that's it.